Okay, 24, power series expansion with integration. If you learn how to compute the Taylor series expansion, you can expand this function that is called the tangent hyperbolic inverse or arctangent hyperbolic. It is a rather tedious job, but it is a straightforward anyway. If you know derivative of log, because it is the definition of log, you can do the job for the derivative, then you will find 1 over x style. So, and 1 over x, you can take the derivative like that and apply this one to this linear combination of these two functions. And they are all computable applying only these formulas. By the way, tangent hyperbolic is defined by sine hyperbolic divided by cosine hyperbolic. And sine hyperbolic is 1/2, like this. Cosine hyperbolic is 1/2 with plus sign. So this 1/2 cancels this kind of form. We first find out this one. This is true because we have this. We have upper bound, upper limit subtracted by lower limit, and subtraction of log is the log of the ratio, right? Because of the 1 plus in here, I can make a change of variable if the denominator is not x, about 1 plus x style, and use the upper limit and lower limit for positive and negative sign, we can reproduce this one. Okay, that's fine. So I can make use of this relation. So I could have taken the derivative to infinity to find out the Taylor series expansion, but there is a much simple way. Because I know 1 over 1 plus t is a sum of power series to sum to infinity. This is true if this y is less than 1. This is not true if it's, for example, t equals minus 1 or plus 1. If t equals minus 1, 1 over 0, it diverges. If t equals plus 1, left-hand side is well defined. However, the representation, power series representation of this fails because we have oscillating series. So I have no way to add this right-hand side is oscillating. So this kind of power series expansion is convergent only if the magnitude of t, the absolute value of the t, must be less than 1. That's fine. However, this provides us with a very simple way to evaluate the power series expansion of this. We know we have converted into this integral, and after we expanding this integrand as a power series in t for any t that has absolute value less than 1, Let's see if it is possible. It expands like that. So this means this x in here is not general, but it should be within the region like that. Okay, in that case, this integral is a trivial. This is t to the k plus 1 divided by k plus 1. What I need to do is substitute plus k, plus x and minus x. We know every even power cancels and odd power only survives as a twice. The reason is that the tangent hyperbolic function is this, and if you substitute minus x for the x, then you have negative sign on it. Therefore, this tangent hyperbolic, sine hyperbolic, both of them are odd functions. And cosine hyperbolic, it is symmetric. So if you replace x with minus x, you will find the same one. So cosine hyperbolic is an even function. Because the tangent hyperbolic is an odd function, you have the factor of 2 in here. And your final result always involves odd powers. This is your answer. Let's go back to the original form. Compare this result with what you would obtain by taking the derivatives repeatedly and substitute the values in comparison with the standard Taylor series expansion. This hybrid method in association with the power series expansion of a geometric series and integration is quite efficient. So it is worth remembering this method. Next, we consider the integral of arc sine. And you can obtain this integral table by making use of the method for inverse function of sine of x. You know, let's say x equals sine theta. And inverse function is defined in the region. There is a 1-to-1 relation with theta from minus 1/2 pi to 1/2 pi. This value of x is from minus 1 to 1. So I draw a straight line and exchange this horizontal and vertical axis. Then what I would get is the inverse function. And it is uniquely defined as long as I choose this region only. So this arc sine is inverse function. We know the derivative of sine is cosine. And in this region, cosine is a single value. Cosine does not change its sign. It is a positive definite in this region. All right, because cosine is a kind of form. All right, so cosine can always be expressed as a square root of 1 minus sine squared. Now, let us make use of this relation. Sine theta is x. So replace everything, every sine theta with x. This is x. This is x squared. And we have made a separation of variables. So left-hand side becomes a trivial integral regarding theta. This is trivially theta. And what is theta? Theta is arcsine. Therefore, this integral is arcsine of x. We make use of this to find this numerical value of this integral. By making use of Newton's generalization of binomial theorem. So 1 over square root 1 minus x squared, that is the integrand of this integral, has the power minus 1/2. And this is 1 plus something, and that something is a minus x squared. And this is alpha. The expansion will give 1 plus alpha delta plus alpha alpha minus 1 2 factorial delta squared, and so on. The formula is identical to the binomial expansion, except that this series does not terminate. It must go to infinity, while the binomial expansion stops at order of this power. Okay, substitute alpha minus 1/2 minus 1/2. Next factor, alpha minus 1, alpha minus 2, and so on. As the number of terms increases, the power of delta increases from 1 to 3, and so on. If you simplify this, you will notice that these factor of 2 increases 1, 2, 3, 4, and your factorial increases 1, 2, 3, 4. In the numerator, we have 1, 3, 5, 7 odd numbers. This is usually written in the form 2k minus 1 factorial factorial. This double factorial notation stands for this the stepping by 2. 1, 3, 5. For example, you have 2, 4, 6, 8. Then you would say 8 factorial factorial. So 1, 3, 5, 7. What's that? This is 7 factorial factorial. Okay. As a result, you substitute the coefficients and you substitute the power to k, and you have to integrate from 0 to x, 0 to x. You know this trivial integral, that is this with this power in the denominator, this denominator. As a result, arcsine of x can be expanded as a power series of x in such a manner. Although it converges very slowly, it absolutely converges.